Let's go ahead and take a look at section 6.1. Now, 6.1 is going to focus on confidence intervals and hypothesis tests when we are focusing on just a single group, specifically their proportion. What 6.1 is going to do that's different that we haven't already seen in chapter 4 and in chapter 5 is a formula now that we can use to calculate or to find our standard error. Now, what this is an alternative to what we were doing in chapter 3, which here I'll just draw a little picture. You don't have to write this in your notes. But in chapter 3, what we were doing is the bootstrapping, where we would have, 1,000 dots, and through that, being many samples, that's how we would get our standard error. What we're doing now is we're going to switch over to using this formula. Now, when you do this formula, there are usually conditions you have to check, and we'll get into that in just a moment. But what I want to do right now is just focus on the formula itself. What it includes is the sample size, which is denoted N. And then you've also got P, which is your proportion, and then 1 minus P, which would be the complement, which is something we saw in section P.1, which is that sort of like the idea of you have 30% chance it's going to rain, then 70% chance that it won't. For the example that we have here, again, it's about just a single group, single proportion. In 2010, when they did a census, they found out that 14.6% of all people living in Oregon spoke a language other than English at home. So that would be our proportion. And then what we'll need for the formula is 1 minus the proportion, which is the complement. So I'm just doing that right here. So 1 minus 0.146 would be 0.854. And then they tell us right here, suppose that we're doing sample sizes of 100. And if we want to get the standard error rather than bootstrapping, the formula asks us to put that information, which would be first the complement, then the proportion, which is the 0.146, times the complement, which would be 154, and then divided by the 100. But then you would do the square root of all of that information. And I want you to try it. This is the time to be getting comfortable with your calculator, making sure it can do what it needs to do. Again, your calculator may need you to put parentheses. It may not. That's for you to try and make sure that you get that squared away with your, again, scientific calculator. Now, if we were to instead do larger sample sizes, again, still same information. There's our proportion, there's our complement. And then now instead we do larger sample sizes of 500. I want you to try that one before I do it. What should happen, this is actually something that we talked about earlier in an earlier section, is that as sample sizes get larger, your standard error goes down. And you should see that from 0.035 drop down to something smaller, which would end up meaning that we're going to have a tighter confidence interval, more narrow, zoomed in to whatever parameter we're trying to investigate. Again, this calculator is for you to make sure you get comfortable with finding the square root key. And again, your calculator may need you to put somehow, some way, some parentheses around the entire information. Okay, but here's what we're going to do. We're going to do some examples where this now gets used as sort of like a embedded step amongst doing confidence intervals, hypothesis test. There's the formula specifically whenever you're using a sample to make an inference about a population. What I want you to notice is that right here is the formula for calculating a confidence interval. But what's different because we have switched to the normal distribution. Remember, it used to be in chapter 3 that it was, 2 times the standard error. And that's when we were doing, 2 deviations to the left, to the right, through the bootstrapping. Now that we've switched to the normal distribution, which is a distribution shape wise that's trying to like mimic or parallel what we were doing in chapter 3, there's some adjustments that need to happen in order for it to match as best as possible with the bootstrapping. And one of those things is that it's not going to be 2 times your standard error in the normal distribution. It's going to be 1.96, which is almost kind of like a 2. But again, the little adjustments are why we see slight differences from 2 to 1.96 is in an effort to try to have the normal distribution and also the bootstrapping be similar in terms of like their shape, their width, and so on. It's just also, if we were to do like a 90%, the way that we would achieve that is by not multiplying by as much to the standard error. So it'd be 1.645. And I'll show you in a second. If you're like, wait, where are these numbers coming from? I'll show you in the normal distribution here. And then for a wider 99 would be 2.576. So as I mentioned, I'll show you. Yeah, if I go over to the normal distribution to show you the way that it lines up for I've got stack key right here, and I go to the normal distribution, and let's say I click the two tail to do a 95% interval. There you see at the bottom, it's got the 1.96 minus, it's got the 1.96 to the positive side. So again, it's trying to like match mirror wise with what we would maybe see in like the bootstrapping. And so it's again, it wouldn't be exactly it wouldn't be exactly 2. So again, just to try to keep it elementary statistics, it's a adjustments that it's making in order to try to match distributions or the shapes of the distributions. Now, as I mentioned, there's going to be a requirement that says, if you're going to be using the normal distribution, which again has a shape something like that, and you want to make sure that your sample sizes are large enough so that if you were to bootstrap it, that the shape of it would be close to the normal distribution, not maybe something like that where they don't match up. And again, to keep this elementary statistics, these are the 2 conditions that we're going to check are satisfied in order for us to have a green light in that the normal distribution is going to be an appropriate distribution for us to be using. And in this example here, it's specifically about a proportion of people who would say that they're, rather than going to the movie theater and watching the movie, that they're just going to wait and watch it at home. And they want us to do a 95% confidence interval for the proportion of people who would more likely just watch at home. Now, what I want you to do, pause the video, and I want you to do these. I want you to find the sample size, like how many people did they talk to? What was the fraction, the p hat? And I want you to turn it into a decimal right there. And then I want you to do the complement, like 1 minus, and it's the right word is not to call it like the opposite. I know earlier I said like 30% chance it rains, 70% chance it doesn't. That's a complement. But I want you to calculate that as well. And again, just pause the video, try those for yourself, and then I'll catch up with you. Okay, so it ends up being that they said they talked to 500 people, and out of the 500 people, 320 said that they're more likely to just wait and watch at home. And that would be our statistic. Now, the other thing we're going to need is going to be the complement, which 1 minus 0.64 would give us 0.36. Now, for the conditions, right? Again, the way that I try to keep it simple is that, we're checking to make sure that our sample size is large enough so that if we were to bootstrap it, the shape of it would be, pretty close to the normal distribution. When they say to check the first condition, that right there that I just circled, that's the sample size n times the statistic, times our p hat, which in other words would be these two multiplied. And all that you're doing is just checking to make sure that when you calculate these two values, that you get something that's 10 or bigger. And again, there's other conditions out there that usually, as you get deeper and deeper into statistics, that you would need to focus on and be concerned about. But for us, this is primarily the furthest that we're going to go in terms of like checking conditions. And look, boom, I'm going to put a check mark. Yeah, that's 10 or bigger. And then we do the same thing with the complement. So you take your sample size and now you multiply it by the complement. And again, as long as you get something that's 10 or bigger, like you're good. Just put a little check mark. Now, already seeing that they did a sample size of 500, that's pretty good. Where would this maybe come into more, hey, suspicion that or concern that it might be too small? Maybe if they only did 50 people, maybe that would be okay. But if they only did like maybe 5 or 10 people, then that might be inappropriate to use the normal distribution, and instead just revert back to using the bootstrapping. Now, for the standard error, the formula's up there. And when you do get to the test, the formulas will be provided. It's not something that you have to be concerned about having on your reference sheet. You can if you'd like, but there it is, right? All I did was just do that, right? The proportion, square root of the proportion times the complement divided by the sample size, which was 500 people. And then again, this is your time to be practicing this. It should come out to be 0.021. Again, we'll do a couple more of these, but what the ultimate purpose of this problem was to get our confidence interval, and they're telling us to use this. Now, because we're using a 95%, like that's the desired width that we want. For Z star, we're going to be using 1.96, which is the one that most reminds us of the confidence intervals we've done in chapter 3. It was times 2 when it was a 95%. So this is going to be 1.96. And we've got everything we need. We've got our statistic, which is the 0.64. Again, we're going to do a minus version. We're going to do a plus version, 1.96. 1.96 times our standard error. And I'll let you go ahead and take a shot at calculating that, or just put in your calculator, make sure you get some good numbers. Again, if it doesn't say whether to round to 2 or 3 decimal places, you could do 2, you could do 3. I'm going to do 3. And then we would do our typical, we are 95% confident. So you do want to have, this little template on your reference sheet as we eventually head into test 3. But this is something that we've already done in test 2, so it's still hanging around. Yeah, that we are still going to need to be doing some confidence interval interpretations. So again, the purpose of this interval or the study was to see what proportion of people who would be more likely to just wait and watch a movie at home And of course, I'm also sure that it depends on, what the movie is. Like if it's the new live action Moana movie, probably gonna wait to just watch it at home if you even do watch it. But if it's the new like Spider-Man movie, yeah, I'm probably gonna go to the theater for that one. All right, so you got 599 again. If you end up using just two decimal places, that's okay. But and then also that I'm okay if you do decide to leave it just as decimals. Maybe on this one I'll do percentage just in case you're someone who's like prefers seeing these as percentages. That is totally up to you. Or if you just want to leave it still as 0.599, don't need that. All right, so that's all that's new. Just this little formula that now is really handy, allows us to get standard errors. There are conditions that you need to check. Will we check them every single time? No, not every time, but if it's ever asked, they'll be given, they'll be provided. You just got to use them. And these things will also be provided as well whenever you get to the test. Just got to know how to use them. And just keep in mind, this is the one that's for your confidence interval. Now, this one here is just a quick self quiz, which I'm not gonna. I don't think I'm gonna do it here for the lecture. It's very redundant to the one that we just did. If anything, what I'll do is I'll real quick give you like an answer key for this one, or if you even want to try it now, like pause the video. The one thing I want to give you a heads up on is that this one is a 99% confidence interval. So when you get down to doing the statistic plus minus z star, that z star is going to be uh, you'll have to go and look back and see what that is. It's not mentioned here on the test. It will be, but it's right there. It's the 2.576. But maybe go ahead and try it. Yeah, if you want to go ahead and just pause the video, try this one start to finish, get your proportion, get your sample size. All right. So hopefully you pause it. If you haven't, pause me, try this one from like start to finish. Um, all right. But here it goes. Here's what I'm going to do rather than, just like for the sake of time, just to kind of keep this video moving. Yeah, things that you should definitely end up having is the 1,500 is how many people that they talk to. And then the proportion of those who said that they were thriving was 0.52. Complement would be 4.8. And then checking the conditions would be that you multiply the 1,500 times separately. You would do times the actual proportion and then the complement. Again, as long as you get something that's bigger than 10, like I would just throw a little check mark on that and say, yeah, we're going to be okay to be using the normal distribution and the formula that's associated with the normal distribution. Um, Here, I'm just going to put the answers. Again, if you do the little square root formula, you should get 0.013, proportion times complement divided by sample size. Then if you do your formula to get your interval, should get 0.487 to 0.553. And then you can finish this one off. We are 99% confident that the proportion of all US adults who are thriving is between 0.487 and 0.553. Yeah, so that one's really, really super, super, super similar to the last one we did. So I'll leave that for you as an exercise. And what I really want to focus on is this one here. This is a hypothesis test where The formula for the z-score, which was introduced in 5.1, is going to be used to standardize our stat. The formula for SE is given. And then the only weird thing about it is like, what in the world? Why does it have a PO there? Well, what's happening here is, remember, we are trying in a hypothesis test to argue in favor of the alternative. Like that, this is the one that we're trying to find evidence for. However, which of the two do we assume is true? Only simply for the sake of argument, in hopes that eventually, as we get further down in the test, we find something that contradicts it. That would be the null, the HO. This one is assumed to be true in hopes that when we get down here, we can hopefully be able to, reject it. So because of that, whenever we get to this part here, which is to calculate the standard error, when you plug in the proportion to calculate your standard error, you're going to use the proportion from the null because it's the one that's assumed to be actually true as we go through this scenario. All right, let's try this one. So they're doing a test to see whether there's evidence that the proportion. Oh, excuse me. That's gonna be the next one. Actually, I'm gonna have you do this next one in just a little bit. This one here is Mendel's genetic theory suggests that under certain conditions, the proportion of pea plants that produce smooth green peas should be 0.1875. A sample of 556 plants from the experiment had 108 with smooth green plants. Test, right? And there's our master word there. Test whether the proportion of smooth green peas differs from 0.1875. So whether the proportion is 0.187 or this is what we're trying to argue for, that it differs from 0.1875. And as far as the sample, what happened was 108 out of 556 had the smooth green peas. And so what we're going to do with this is go ahead and divide it. And that right there is our statistic. Now, in the last examples, what we did was we took the statistic and that went into the formula. But right now, we're living in a moment where the assumption is that the null value is true, that this right here is actually true at the moment. So when you come here, you're actually going to take that and plug it into the formula to get your standard error. Now, what I want to do, let me just find a spot. Maybe, I don't know, maybe I'll just do it right here so we can have it on our screen. 1 minus 1875. Just somewhere real quick, just to show you. Yeah, we're going to need the complement. 0.1875, which is 0.8125. That's our complement. So we could put the proportion, which is the null proportion, times its complement. I put my decimal right here, make sure that looks like a circle, a 0, over 556. And then when putting this in our calculator, we should get 0.017. Now, this one we're not doing confidence interval. What we're going to do now is standardize this. And that's the little formula that they have on top, which is the statistic minus the null over the SE. And we've got all three of those numbers. We've got our statistic. We've got our null value. And we've got our standard error that we just got a few moments ago. And you would put this into your calculator and see what you get. Now, again, you might have a calculator that requires to maybe put parentheses around this or to do the subtraction first, but we should get 0.38. And if you've already been working on your 5.1 homework, that's great. That means you've already been using the normal distribution. But I'm going to go ahead and get us into the normal distribution to get our p-value. And again, it's guiding us. It's saying, take that, go to the normal distribution. So the point rate, and also real quick, we're doing a two-tail test. So remember, for two-tail tests, we have to make sure that with the p-value, we do the times two. But let's go over there to the normal distribution. I'm just gonna wipe it clean and do two-tail. And then at the bottom, we got negative numbers, we've got zero, we've got positive numbers at the bottom, and it's right here on the bottom right that we're going to put the 0.38. I just went and touched there, and right there I'm going to put 0.38. So again, we're trying to see how extreme that the observed value is, and we're getting a 0.352. That is the p-value, but only half of it since we're doing a two-tail. In other words, we need to take the 0.352 and do times 2, which is just taking both tails and joining them together. So the p-value would be 0.352 times 2, which is 0.704. That is our p-value. And I want you to take just a few moments to think about what a p-value would like that size of p-value would do if we're using a 5% level of significance. And think about, what we've been doing in chapter 4, chapter 5. If a p-value is really large, can we reject the null hypothesis or not? And the answer is no, because that is too large of a p-value, indicating that there's a large possibility that it may have just been a fluke. So we're not able to reject the null hypothesis, or you could also write there, there is not a fail to reject null hypothesis. There is not enough evidence to suggest or to support that the proportion, and all I'm really doing here is just borrowing the words from what the test was about. It was whether the proportion of plants with smooth green peas differs. In other words, there's not enough evidence to argue against Mendel. Mendel might still be right. We're not going to say we accept Mendel's theory. We just don't have enough evidence against it. All right. Now, if you scroll on, you'll see that this one here is an example noted as being a quick self quiz. So I do want you to try this one on your own without me, which would mean maybe go ahead and pause the video. All I'm going to do real quick is just give you a couple little, you're doing your HO, your HA based on what's being tested. You're going to do your proportion. And that's what in 6.1, everything is proportions, single proportion. Then for when you get here to do your standard error, remember the pooled proportion is whatever proportion is right there. And you'll need you'll need you'll need the complement, you'll need the sample size. You might also just take a quick moment as you're getting this one started to put, what's the sample size, and then maybe sneak in the proportion, the complement, just somewhere where it's not going to be in anybody's way. And then for your Z, yeah, it's up there. The little formula for Z is there, but do the whole shebang. Whatever you get here is what you're going to put into stat key to see if you get a small enough p-value or not, and then from there make your conclusions. What are you going to say about HO? Reject or not reject HO? There is or there is not enough evidence, and then put the context. But let me be quiet, and you just pause the video, try this one on your own, and then I'll give you the answers. All right. So hopefully you've had an opportunity to try that one on your own. They were testing whether the proportion of teams that win the coin toss would win more than 50% of the overtime games. And again, I'm going to suggest that rather than putting the percentages, I may already have said this in another video. If not, I'll say it now and also in the future. Just go and put them as decimals, because whenever you end up using this down here and then down here, it's nice to already have it in decimal form, because several of the other numbers are already going to be in decimal form. What happened with the sample was that 240 out of 428 did win the overtime, which that would be our statistic, 0.56. And then here's you got to be careful. And the homework will remind you that when you're doing your standard error, at the moment we're assuming what's true is that the proportion is only 50%. So that's what's going to go into your standard error calculation. 0.50 times. And then right here is what we would usually put, the complement. I'm just going to do it right over here to the side. If we're doing the complement of 0.50, well, that's 0.50. And we got to make sure we put the correct number here, which would be the sample size, 428. And that gave us 0.024. And then we're going to take our statistic minus the null. So again, there's our statistic, there's our null value. Then we've got our standard error that we just got a few moments ago. And this should get you 2.5. And again, I hope right now everybody feels, yeah, you're totally okay with the subtraction division there to get that 2.5. Now, you got to remember how to recognize when you're doing left tail, right tail, two tail. This is a right tail because it's greater than. We might as well even just write it here. Right tail, and 428 was our sample size. But let's go ahead and do it. Let's take the 2.5. Just going to erase this and do the right tail. And down at the bottom right is where you put your there's our p-value. Now, if you haven't done the conclusions yet and you're seeing the 0.0062, that will sometimes be on test 3, test 4, whenever they just give you the p-value and you just got to use it. So let's say this was like, boom, just given to you. Like, what would you do? Would you reject HO? Would you not reject HO? That is very small. Even more so, it is smaller than an alpha of 1%. So the likelihood of the result that they saw from the sample being a fluke is really, really small. So we're definitely able to reject the null hypothesis. So this just died, right? The idea that only 50% of the teams win the overtime if they get the coin toss doesn't seem to hold water. Now, you can say if all you said was there is enough evidence, you're good. But we could also, because the p value being so small, say there is strong evidence. Remember, the smaller the p value, the suggestion is that it was not a fluke, and so that was like not a fluke, not a fluke, given a strong evidence that suggests that the proportion of all NFL teams that win the coin toss or the coin flip will win more than 50% of the time. Specifically the OT games, the overtime games. All righty, but that is it. Again, so it's 6.1 is a nice lecture because it reminds us of confidence intervals, hypothesis tests. It allows us to reuse, get further comfortable with the normal distribution, p values, and but now what it's got is embedded a formula that helps you get standard error for a single proportion rather than bootstrapping, as long as the conditions check out. But that is the end of this recording. I will go ahead and end it there, and again, reach out to me if questions come up.